Good morning, everyone, and thank you for attending my talk entitled The Northeastern BC Montney Tight Oil Play Potential and Challenges. So I wanted this title to be catchy, but I did not realize until I started building the story and putting together those slides how ambitious it actually was, and it ended up being a lot more work than I initially envisioned. Anyway, I hope that this presentation will hold up the promise of its title and that it will be informative and useful for most of you. And before moving on to the agenda of the presentation, I would like to acknowledge my co-authors, Neil Watson and David Cronkwright from Enlightened Geoscience, as well as Albert Cui and Jordan Wilson from Agat Laboratories. Integration is not just a buzzword, it is actually a necessity to understand complex and conventional hybrid systems such as the Montney play, and it is only through collaboration that we can minimize bias that we all have from our technical background and preconceived models. Here is the agenda of our presentation, starting by a couple of slides to set the stage with the geological setting, as some of you may not be familiar with the Montney play. Then we will move on to demonstrate how we define the Northeastern BC tight oil fairway. Next, I will show you some production data from over 300 wells to illustrate the wide range of well performance in the tight oil fairway. And finally, we will look at some of the geological controls on this variability and how integrating geology, geochemistry, hydrodynamics, and PVT data can help de-risk the play. Okay, let's start with a few words on the geological setting. The Montney Formation is a thick sedimentary wedge that was deposited in shallow marine and shelf depositional environments along the western margin of the Pangaea supercontinent during the lower Triassic. The map on the right illustrates the present-day subcrop extent and thickness of the Montney Formation, bounded to the west by the Canadian Cordillera Thrust Belt and to the east by an erosional subcrop edge. And the blue outline shows our study area that corresponds to the northern part of the play in western Alberta and mostly in northeastern British Columbia. Here is a more detailed isopack map of the Montney Formation in our study area with major structural elements derived from Berger work based on aeromagnetic and seismic data. It shows two major depot centers, respectively, in the Peace River and northern Montney areas. It is important to understand the structural framework because it not only controls the deposition of the Montney Formation, but also its burial history, including diagenesis, pressure compartmentalizing, and gas migration pathways, as I will illustrate later in this presentation. On the right side are two deep-oriented regional cross-sections illustrating the depositional environment, which, as you can see, mostly consist of offshore transition deposits in orange, locally interbedded with turbidites in brown, and several types of bioclastic deposits in blue and purple. In terms of grain size, the Montney Formation mostly consists of dolomitic and feldspathite medium to coarse grain siltstone, but reservoir quality is strongly affected by post-depositional diagenetic cementations as well as solid bitumen plugging the porosity. Due to its large thickness, the Montney play is developed through multiple production benches stacked vertically, as illustrated by the blue dashed outlines corresponding to the drilling targets in various fields along those depositional cross-sections. I also superimposed the fluid-type fairways along those cross-sections, and as you can see, the liquids-rich gas fairway is much larger in the northern Montney area, and I will expand further on that in the next few slides. Okay, let's move on to the next part of this talk and focus on the definition of the Northeastern BC tight oil fairway. Defining fluid-type fairways in an unconventional play requires an understanding of thermal maturity that is commonly estimated using proxies such as pyrolysis Tmax or vitrinite or bituminite reflectance measured from rock samples. Although those tools are very useful to define broad thermal maturity trends and also to calibrate other methods, they don't provide enough granularity due to the scarcity of data points. Furthermore, these methods don't provide any information on fluid migration, which is a key element for the understanding of unconventional hybrid plays such as the Montney. Gas compositional mapping, on the other hand, has proven to be a powerful tool in recent years to decipher in situ fluid distribution in the liquid-rich gas window. The map in the center of this slide illustrates spatial variations of early production gas dryness, which is a ratio of C1 over the sum of C1 to C5, in the upper Montney over a study area based on over 2200 data points. As you can see, it provides a much more detailed picture of in situ fluid distribution and allows for drawing important conclusions when combined with the regional structural framework. First, the width of the liquid-rich gas fairway is much larger in the northern Montney area, as was also illustrated along the regional cross-section in a previous slide, and it suggests a change in the geothermal gradient across a river fault zone. And second, besides the thermal maturity gradient, this map also reveals gas unreached fairways along which in situ fluids are drier than thermal maturity would predict, and that are interpreted as gas migration fairways. And some of those gas unreached fairways that we highlighted with white arrows are very well aligned with major basement-involved strike slip faults that likely influence the updip migration of gas. And the graph on the right side illustrates the comparison of the gas dryness with available ethane and propane isotope data from produced gas, and show that our mapping is consistent with equivalent vitrinite reflectance based on the calibration from GeoMark research. So integrating this mapping with other geochemical proxies listed in the table on the right, we were able to define and map the Northeastern BC tight oil play that is bounded by the updip limit of the condensate gas window derived from our gas dryness map to the west, and to the east by the 10 kPa per meter gradient defining the overpressure deep basin. It covers an area of approximately 9,000 square kilometers and has only been drilled by less than 400 horizontal wells, 40% of which in one single area, the Tower Parkland oil field. As illustrated on the map on the left, the vast majority of Northeastern BC Montney horizontal wells were drilled in the liquid-rich gas fairway of the play so far. Now that we have defined the Northeastern BC tight oil fairway, let's have a look on some production data. On the map on the left, the color scheme represents the first year cumulative oil production. So it demonstrates that well performance is highly variable both at local and regional scale within the tight oil fairway. Good wells commonly exceed 50,000 barrels of oil the first year, up to nearly 200,000 barrels for the best in class. However, there are also poor oil wells and even some dry gas well or other wells suspended during the first year, corresponding to the orange, red, and gray colors on the map. This map also further illustrates that we are still at an early stage of development of this tight oil fairway, and that there is a lot of room for growth, but de-risking is still needed based on the highly variable well performance so far. As mentioned at the beginning of this talk, due to its large thickness, the Montney play is developed through multiple stacked production benches, and this slide illustrates which stratigraphic intervals are currently targeted in Northeastern BC tight oil fairway. The graph on the right shows 1 year cumulative oil and gas production normalized to the frac length. It shows that the development so far has mostly been focused on the upper Montney in red, that represents more than 80% of the producing wells. However, the middle Montney in orange and yellow was also targeted by a few tens of wells, some of them with very encouraging results. Only 4 wells targeted the lower Montney in green, with comparatively poor results in terms of oil recovery. And we can go one step further and look at the different production benches within the upper Montney as illustrated on this slide. And it showed that the upper units M34 and M35, respectively in pink and orange on the graph, have among the best oil recovery, which may suggest that these intervals have a better reservoir quality. Now let's have a quick look on the influence of some of the stimulation parameters on oil recovery. These graphs represent the normalized one-year cumulative oil as a function of fluid intensity on the left and proppant intensity on the right. The graphs show no clear correlation even within single stratigraphic units. However, one can note on the graph on the right that the maximum oil recovery increases with increasing proppant intensity up to about 1.7 ton per meter, beyond which there seems to be no additional value. Overall, this slide illustrates well that geological controls have a strong impact on oil recovery that tend to blur any relationship with stimulation parameters, which provides a good transition to the next part of this talk, focusing on geological controls. But let me introduce first a key concept to understand controls on liquid recovery in unconventional plays, which is production fractionation. As simplistically illustrated on this slide, unconventional reservoirs have pore size distribution orders of magnitude smaller than conventional reservoirs, which results in strong interactions between hydrocarbon molecules and pore walls, and even more so for larger molecules. Thus, those larger molecules and more polar compounds tend to be preferentially retained in the reservoir, resulting in produced hydrocarbons being leaner than in situ fluids. That is what is illustrated on the left side of this slide, and I listed in the middle some of the physical processes that are invoked to explain this fractionation, including differential adsorption, molecular sieving, pore confinement effects, and of course fast separation when the reservoir pressure goes down below the saturation pressure of in situ fluids. And on the right side of the slide are listed key controls that influence the extent of production fractionation, including reservoir pressure and temperature, reservoir quality, well and stimulation design, as well as near wellbore depletion during production. A way to evaluate the extent of production fractionation is to look at geochemical proxies like gas dryness and Stockton or API gravity that give you an idea of in situ fluid composition, and then compare it with the initial gas oil ratio during flow tests. So this slide illustrates 5 flow tests representative of the different thermal maturity windows, the red curve representing the GOR, and the gray curve the casing pressure. The blue dashed line is where we picked the initial gas oil ratio. So to illustrate production fractionation, I would like to draw your attention on well D. In this case, the dryness index and oil gravity both point to the late condensate to early wet gas window, also confirmed by our compositional mapping, but the initial GOR over 100,000 cubic feet per barrel is typical of the dry gas window. Based on geochemical proxies, in situ GOR should be in the 5 to 10,000 range, and the very high production GOR is likely due to production fractionation. Another example is illustrated by well E. In this case, the initial GOR of 1300 cubic feet per barrel is consistent with the geochemical proxies and indicate the oil window, but the GOR increased rapidly to over 10,000 in 200 hours during the test, suggesting strong production fractionation in this case as well. We can thus plot geochemical proxies of in situ fluid composition as a function of initial flow test GOR to evaluate graphically the extent of production fractionation. And that was the topic of our EOTech presentation 2 months ago, and I invite you to look at our manuscript if you want to learn more about this method. Now let's come back to our focus today and compare 2 wells producing from the upper Montney in the Northeastern tight oil fairway. As you can see on the right of the map, well A and B have likely similar in situ fluid composition based on geochemical proxies as well as their initial flow test GOR, but very different outcomes. Well A produced 200,000 barrels of oil, while well B was suspended after producing short of 6,000 barrels of oil. If we look at the flow test of those two wells, well A had a stable GOR at 1,000 cubic feet per barrel, whereas the GOR of well B increased continuously for 150 hours up to nearly 15,000 cubic feet per barrel, suggesting strong production fractionation associated with near wellbore depletion. Another striking difference between those two wells is reservoir pressure. Well A is close to 28 MPa, while well B is in the 17-18 MPa range. The green and red dashed lines on the graph on the right are respectively the bubble point and the dew point curve regression lines derived from Montney PVT data. That is also discussed in some details in our UTech paper if you are interested. Based on this graph, well B was initially very close to the in-situ fluid saturation pressure, and further depletion near the wellbore likely resulted in phase separation and a drop in relative permeability to oil once gas critical saturation was achieved. Well A, on the other hand, was more than 10 MPa above the bubble point as a stable GOR during the flow test and turned out to be an excellent oil well. Before wrapping up this presentation, let's have a quick look on the Tower Lake Parkland oil field, which is by far the most mature area of the Northeastern BC tight oil fairway. It is a busy slide, but it provides a good summary of some of the geological controls on oil recovery. The colored part of the map to the south corresponds to the gas dryness in the gas window, and the uncolored northern part of the map corresponds to the oil window, where the gas dryness was not mapped due to the strong pressure dependency of solution gas. In the gas window, the gas dryness decreases up deep with thermal maturity, but is also influenced by gas migration pathways as illustrated in previous slides and highlighted on this map by dashed red arrows. Some of these gas migration fairways must carry on into the oil window and likely influence in-situ fluid composition and oil recovery. The green lines in the Tower Lake Parkland field illustrate the down-dip increase of oil API gravity with thermal maturity within the oil window. The colored dots correspond to the average 6-month GOR of each well and clearly show areas with higher GOR, likely controlled by geological factors that may include thermal maturity, gas migration, reservoir pressure, reservoir quality, or any combination of those factors. So to wrap up this presentation, here is a summary of practical approaches that we developed to account for geological controls on in-situ fluid distribution and production fractionation, aiming at de-risking the play in terms of potential for liquid recovery, both in the liquid-rich gas and in the oil fairway. Oil and gas geochemical proxies and flow test data were used to define an in-situ GOR baseline and assess the extent of production fractionation. Then saturation pressures were computed based on an equation of state model derived from PVT lab data and recombined fluid compositions, and you can find more about that in our UTech paper as well. And finally, compositional and pressure mapping accounting for the stratigraphic and the structural framework are combined to identify areas with higher potential or risk for liquid recovery. Okay, it's time to conclude now. So in summary, Northeastern BC hold a vast underexplored, overpressured Montney tight oil play extending over approximately 9,000 square kilometers. The tight oil fairway was defined by fluid geochemical and reservoir pressure mapping. The upper Montney has been the main focus of operators so far, but the middle Montney shows good potential too. Production data from over 300 wells demonstrate highly variable well performance that cannot be explained by stimulation design alone. De-risking the Northeastern BC tight oil play requires an understanding of geological controls on both in-situ fluid distribution and production fractionation. And this understanding can be achieved through the integration and mapping of geochemical, hydrodynamic, and production data within a well-defined structural and stratigraphic framework. And that's all I had to share with you today. So I'd like to thank you very much for your attention, and I will do my best to entertain any question you might have. Thank you very much.